Let's look at the computation of a line integral. Our line integral here is written in differential form. So for instance, say we're interested in computing the line integral of y minus x dx plus 2x minus y dy about the curve C. In this particular case, the curve C is the boundary of the following region. Now, I went ahead and drew the region just so we'll have a visual of this. So basically, x runs from 0 to 3, and y runs from x squared minus 2x to x. And so this is our picture, very simple to draw. But if we want to utilize our new result, Green's theorem, one of the hypotheses states, so that the signs work out correctly for the area integral here, is that we have what we call a positive traversal. And the easy way to remember that is, as you traverse the curve, the region R is to the left. Now that's an arbitrary designation, but it is useful and it is needed to preserve the correct signs. So again, in most cases, we don't have to worry so much about traversal or about orientation of a curve, but for this particular theorem, we require that the curve have the positive orientation or the positive traversal. That is, the region R always lies to the left. And so now what we can see is this would require parametrizing two pieces here. So what Green's theorem says is, for this line integral, substitute the following double integral. So now what we can see is our m is y minus x, and our n is 2x minus y. And we need the partial of n with respect to x, which is 2, and we need the partial of m with respect to y, which is 1. What you see is this is just the third component of the curl. When we compute curl, this is the third component. And we know when these two partials are equal, we have a conservative vector field when the vector field lies in R2. So now what we can see upon application of Green's theorem, we just have a 2 minus 1, so the integrand just reduces to 1. And of course our limits for R will be 0 to 3, and of course here, x squared minus 2x to x. So this leaves us with a very simple integral. So now we just take the difference of the limits for the y integral, and we get x minus x squared minus 2x. The negatives absorb, so that'll give us a 3x minus x squared integrated with respect to x. Very, very simple integral. So you can see that Green's theorem is saving us quite a bit of time. And so now add 1, divide by the new power, we get 3 halves x squared. Do likewise here, we get a negative 1/3 x cubed. Evaluate from 0 to 3. Of course, the lower limit zeroes out everything, so we don't have to worry about that. But when we substitute the 3 in this particular term, we get 3 times the 9 divided by 2, and then of course we get a negative 1/3 times 3 cubed. Notice here the 3 divides here, leaving us a negative 9, and so we need a common denominator of 2, so that'll give us a 27 minus an 18 divided by 2, which is 9 over 2. So again, what we can see here is that the result of Green's theorem is one of great importance, and we're also going to see that we're going to be able to flip this idea and actually be able to compute areas using the line integral. So what we often do with these vector calculus theorems is we focus on the particular integral that's easiest, and then we try to maximize the result by doing such. And we are done.